the moment we are discussing heat exchanger, and in the last class, if you remember that we for the heat exchanger, uh, so we have started the heat exchanger chapter, which is chapter number 13 of your book. So in the last week we discussed about first of all we discussed about different types of heat exchangers. So we know that there are different types like uh, first of all double pipe heat exchangers. Then we have got compact heat exchangers, and then shell and tube heat exchanger. There are many other heat exchangers, but we are only considering these three at the moment because they are more frequently used in the industry. And then afterwards we discuss about overall heat transfer coefficient. And if you remember that we represent it with U, and for the case of heat exchanger, if we talk about the overall heat transfer coefficient, so let me first of all, if I can kind of show you the figure that okay, ji. So at the moment we are considering this double pipe heat exchanger. If you look here closely, that we have got two pipes here. One is the internal pipe in which we would have some flow of fluid, and then there is some gap between internal pipe and external pipe. So that is the place where the fluid the other fluid would pass through. And then you can see easily the thickness of this inner pipe. So basically we have got three resistances in terms of heat transfer. So if we talk about those resistances, so first of all it would be or convection of interior this internal fluid, and that would be equal to 1 upon hi into ai. And what is ai here? Ai is the surface area, and that would be equal to 2 pi di into length of the pipe. Length of the pipe is this length of the pipe. Then we have got our conduction, which is the uh, conduction resistance through this thickness of the internal pipe. So that would be equal to natural log of d out upon d in divided by 2 pi kf time. And then this was the resistance for the so this is the first resistance, second resistance, and then the third resistance would be R convection outer fluid. So which is passing through this annular space. So that would be equal to 1 upon H outer into A outer. So A outer here is 2 pi. Sorry, I think here it should be not 2 pi but only pi. So I would pi di. So here I would also, it would be pi into d outer into length of the pipe. Length of the pipe is this length. So this is the length of the pipe. Okay. So now if we know that, if we consider the radial heat transfer, we have got three resistances in series. So if we want to show them here, it would be So this is T infinity outer, this is T infinity inner. And here we have got R convection outer, then we have got R conduction, and then R convection inner. And we know that if we want to calculate the total resistance, we can say R of total is equal to these three resistances, which can be written 1 upon H outer, A outer, plus natural log of D outer upon D inner divided by 2 pi Kl plus 1 upon H inner into A inner. And then we also know that this is equal to 1 upon UA, right? So U can be on the inner radius or the outer radius of the. So it means that here we can also write UIAI, or it can be also equal to 1 upon U outer into A outer. So it all depends that how do we want to define this overall heat transfer coefficient. So all this discussion we have done in the last class. So we also know this relation from chapter number 3, because in chapter number 3 we also discussed about overall heat transfer coefficient. Now there is one additional resistance in the heat exchanger, because this discussion is only applicable when we have got new heat exchanger. It means that there is no accumulation on these pipe surfaces. So because you know that with the operation of heat exchanger, there is some kind of corrosion, there is some kind of bacterial growth on the pipes because of that chemical reaction. So we have got that deposition of some substance on the pipe surface. So that deposition of substance on the pipe surface, that is called fouling. We call it fouling phenomena. Fouling is basically deposition of material on pipe surface. Right. So now this deposition, okay, just a very easy question, that whether this deposition would increase the thermal resistance or decrease the thermal resistance. Anyone? Whether it would increase or decrease? जी शादी ओके, आपकी आवाज कट रही है. इफ यू कैन रिपीट शादी और हैदर फॉर दैट इंस्टेंस. बेटा आवाज कट रही है आपकी. इट इज नॉट ऑडिबल टू मी. हैदर, कैन यू tell us something? So I think Shahriz was Shahriz wanted to say something. So increase karegi. Thank you very much, Shahriz. So it means that this fouling phenomena would increase the thermal resistance of this heat exchanger. So now, first of all, we would look at different types of. Yes, I can hear you, Shahriz. I can hear you now. It is better this time. So, thank you for your contribution. So, let's talk about fouling now. Fouling. As I have told you that fouling is the deposition of some external material or substance on the pipe surface, or whether on the interior surface or the exterior surface of the inner pipe. So now fouling has got three different types. One is called precipitation. It is the accumulation of some solid on the pipe surface. On pipe surface. And this kind of fouling usually happens when we use hard water, for for the flow uh, for for the flow inside the pipe. So in that case, some kind of particles would deposit on the pipe surface. So that is the precipitation. Then the second one is the chemical fouling, or we also call it corrosion. So, corrosion phenomena, we also know that that is quite evident, and we can see it on the pipe surface. So whenever we kind of passes the hot water, very warm water through some steel pipe, then there is always a possibility of corrosion. So that happens with the passage of time. It normally doesn't occur in uh, first couple of years, but rather when we have got the constant operation, then we have got the due to chemical reaction. So this is due to chemical reaction. And then the third one is the biological fouling. So that is when we have got some bacterial growth on the pipe surface. Right, so we have got these three types. So for to avoid corrosion, what we need to do, that we can use some plastic pipes, or we can do some kind of chemical treatment on the pipe surface. And similarly, to avoid biological fouling, we can also do the chemical treatment of the pipe surface. Right. So let me show you the that picture of pipes having fouling. You can readily see that there are some kind of substance deposition on the exterior of these pipes. So we can clearly see that there is some kind of corrosion on the left hand side figure, and on the right hand side we have got some deposition of some substance on the pipe surface. So uh, now, how to quantify fouling? That is being done by the fouling factor. So it means that if we want to know that how much additional resistance has been offered by this deposition, so for to measure that, we use fouling factor. So fouling factor is a measure of thermal resistance introduced by this deposition. Yes. Anything you want to add? Bilal Ahmed Ijaz, anything you want to add? Okay, maybe not. So, as we discussed about three different types. One is precipitation, the accumulation of solid deposits in a fluid flow on the heat transfer surface area. On the inner surface of the T-board, you can also see some kind of that deposition. Then hard water results in the accumulation, and it can be cleaned by chemical treatment of the pipe. And then corrosion, chemical fouling. So we all know that it happens, okay, due to chemical reaction between the pipe surface and the warm water. And then we have got biological fouling. So it is due to the growth of algae, and fouling usually fouling increases with with increase in temperature and decrease in velocity. Because if the velocity is less, then there would be more time for that solid to deposit on the pipe surface, and if the temperature is more, then there would be more chances of chemical reaction between the pipe surface and the water. Okay, so that is the chemical corrosion. Now, as we discussed that we need to count for that addition resistance, so that is done by this fouling factor, and it is always given in meter scale into Kelvin per meter square Kelvin per watt. So meter square. So usually, if we look at the definition of U, so and just a minute, let me show that U definition here again. So here we would have 1 upon U A would be equal to R total, which would be equal to, first of all, the interior resistance 1 upon HA, HIAI plus uh, natural log of D outer upon D inner 2 pi KL plus 1 upon H outer A outer. Now, if you see this, because R is basically equal to delta T upon Q, right? So the unit here is Kelvin per watt. So if we want to introduce this RF, then we need to divide it with area to get to have this equation having the same unit. So here we would say RFI and RF outer divided by A outer. Right? So I have explained that because the unit of RF is meter square into Kelvin per watt, while the unit of resistance in this formula they are only Kelvin per watt. So if we want to write this RF into this equation, we need to divide this with the area. So that's what we have done here. So this is the fouling factor on the internal pipe and on the internal side of the pipe, and then this RFO is the is the fouling resistance on the outer side of the pipe. Okay. So this we have discussed, and now I can show you and then I can show you the fouling factor for some um, common pipe surfaces. So if I can maybe able to zoom it a little bit, a minute. This equation we have already discussed that we have included RFI plus RFO in this division by the area, and then you can here you can see the unit here is meter square into Kelvin per watt. So usually the unit of resistance is a Kelvin or centigrade per watt. So that's why we have to divide it with area in the calculation of total resistance. And after that, there is some kind of fouling factor which is given for distilled water, seawater, river water, for the boiler feed water heater. If the fluid is fuel oil, then the this uh, fouling resistance or fouling factor would be 0. So basically, it is exponent minus 4. So all these values are exponent minus 4, order of exponent minus 4. So now we can, in a numerical problem, we can see that how much difference it would make. And secondly, the point of emphasis here is that this fouling phenomena happens when the heat exchanger is being in operation for a long duration of time, because the accumulation of any solid or chemical corrosion happens with the passage of time. So it never happened on a new heat exchanger or boiler. So that's why we need to clean those pipes by using the chemical treatment, because we want to reduce the fouling phenomena so that the heat transfer would be more effective, because the purpose of the sole purpose of any heat exchanger is to have maximized heat transfer between two fluids, right? So that's why we need to do the periodic maintenance of those pipes by chemical treatment to reduce fouling. So that is what usually we inside the industry people do for boilers and condensers. So then this now we can do one numerical problem where we can see the effect of fouling. So here the statement of the problem is a double pipe heat exchanger. It is constructed by copper. Thermal conductivity is 380 watt per meter Kelvin, and inner tube of the internal inner tube of internal diameter, which is 1.2 centimeter, and external diameter of that inner tube is 1.6 centimeter, and an outer tube of diameter 3 cm. So it means that we have got, if I show you uh, the side view of that, we have got one pipe, and then we have got a bigger pipe outside, right? So uh, this diameter is, I think, if I show you the, so DI is 1.2 centimeter, this is 1.2 cm, this is 1.6 cm, and then this is 3 cm, right? And then one fluid is going to go through here, that is the, and the other fluid is going to pass through this way. And usually we take the outer surface to be perfectly insulated. So this surface is usually insulated. So all the heat that is being transferred between these two fluids and nothing is being lost to environment. So that's why we want to insulate this heat exchanger. So now this is given, and what else we have been given here? The convection coefficient is given, that is reported to be Hi. It means that inside this pipe, for this, here it would be Hi, and here it would be Ho. Okay? Because one fluid is going from here and one fluid is going inside the pipe. And then for a fouling factor, now fouling factors are given on the tube side and on the shell side. So shell side is, you can call it, this is shell side and this is tube side, which is this. So those fouling factors are given. So thermal resistance per unit length we need to calculate. So that is quite easy. That we can say that R, sorry, I think we can use black pen for this. So R total would be equal to, so first of all, if we start from here, first of all, it would be a convection resistance of the internal fluid, that would be 1 upon Hi into pi di, right? And L is 1 here. Plus, here there would be some fouling, that would be Rfi divided by pi di, which is the area into length. Length is 1 in L is 1 meter. Plus, we have got conduction resistance, that would be equal to log of d outer upon di. What is d outer here? That is 1.6 centimeter. D inner is 1.2 centimeter divided by 2 pi into k. Length is again 1 meter plus RFO, which is the fouling here. If I can show those fouling. So that is the fouling here, and one fouling is somewhere here on this side. that is the deposition of some. So this is also due to the form. Right. RFO upon pi d outer plus 1 upon h outer pi d outer. And d outer is 1.6 cm. So now we know HI, RFI, DI, D outer K is given for the copper pipe, and then H outer is also given. So if we put in the values, we can the easily calculate the value of R, that is 0.0837 centigrade per watt. So this was by considering the that chemical fouling. Now the overall heat transfer coefficient Ui and Uo based on the inner and outer surface area of the pipe. So it means that first we calculate R total. Now if we want to calculate, now R total is equal to 1 upon Ui into Ai is equal to 1 upon U outer into A outer. So it means that this is the overall heat transfer coefficient based on this internal surface area, and this is the overall heat transfer based on this external surface area of this pipe. So if we calculate Ui, then that would be equal to R total into pi d I, and similarly U outer would be equal to R total into pi d out, right? So we can calculate this. So one thing you can do here, that if you neglect these two fouling factor terms here, then you can also calculate the value of R, and then you can see that here it is 0.0837. So in that case, maybe it would be 0.05, around 0.05, or maybe 0.06, depending upon the value of RFI. So it means that by the consideration of this fouling factor, the total resistance usually, or all the time, it always increases. So we can calculate Ui, and then also we can calculate U outer. So that would be equal to this. So I think we have, it should be, I think Ui would be 1 upon this. I think we missed that Ui would be equal to 1 upon R total into this, and U outer 1 upon R total into pi d outer. So we can easily see that the value changes a little bit, 317 and 238. So that's why when we talked about the value of U, you can easily see that that value is depending upon that ranges. It is not the exact value. So that exact value, so because it is kind of in a range of like 200 to 400, we can say, for this case. Okay ji. So up to now we have talked about two things. One is type of heat exchangers, and the overall heat transfer coefficient. And the last thing I want to add here is that if we want to calculate Q here, then usually we use HA into uh, HA delta T. So delta T can be logarithmic, it can be Ts minus T infinity. But when we talk about heat exchangers, then this formula becomes U into A into delta T. Now we are going to use this formula, U into A, because now we have got an additional resistance of that conduction resistance of the pipe. So that's why we are using U here, because we have to accumulate all the resistances and as well as the fouling effect. So now we are going to start heat exchanger. analysis. That how do we determine whenever we do heat exchanger analysis, we have got one of the two options. Option number one, that we are being given a heat exchanger, or we can buy it from the market for that matter, and we need to determine the change in temperature for the hot and cold fluid. So uh, here the purpose is to determine the change in temperature for the hot and cold fluid for a given size of heat exchanger. Okay, it can be very big heat exchanger, it can be very small. Okay, so one purpose of doing analysis is this, that we need to determine the change in temperature for the hot and cold fluid. Second thing is that a change in temperature. And so, if we want to know that whether that how much size of the heat exchanger is required to produce that change in temperature, right? And so it means that we can here write that size requirement for a given change in temperature. So this is the uh, we need to determine the size of the heat exchanger. The second purpose is that here we have to uh, here we have to design the heat exchanger in a way that we need to determine that how many turns and length of the pipe of the that tube is required. So here we are designing for the size for a given change in temperature. The second bit is that size of the heat exchanger is given. Size of heat exchanger is given along with the inlet temperatures of hot and cold fluid, and we need to determine outlet temperature of hot and cold fluid, right? So these are the two things which we need to do in this. So these are basically the two purposes for which any heat exchanger analysis is performed. Now, in the first case, let me repeat it again. In the first case, uh, the temperature uh, which is going to be required to be changed for the hot and cold fluid, that is our input parameters, and we need to determine the size of the heat exchanger which is needed to have that change in temperature. So change in temperature is the I can say input parameter, and this size requirement of the heat exchanger is the output parameter. Okay? And this is done by the analysis which is called, usually we do it with LMTD method. LMTD method. What is LMTD method? Log mean temperature difference. Okay, log mean temperature difference. We are going to discuss it in detail in the coming hour. And then for the second option, we are given the size of heat exchanger as this is input parameter, and that along with the inlet temperature of those two, and then we need to determine the outlet temperature. Sorry. Outlet temperature. So these two things. So these are the output parameters. So that is what we are going to determine, and this is done by effectiveness NTU method. The first design analysis is done by the log mean temperature difference method, and log mean temperature difference we have studied in flow over tube banks, and for the internal flows when we have got constant temperature boundary conditions. So in that case we discussed about Q is equal to HAS delta T logarithmic, right? So like in the quiz which I gave last week, so in that, because the temperature boundary condition was constant temperature, so we needed to use log mean temperature difference in the formula. Q is equal to HAS delta T log mean. So now we are going to discuss these two methods. So in this week we are concentrating on log mean temperature difference, and in the next week or so we would be discussing the effectiveness NTU method. Okay. Before we go on to the analysis of these two, there are certain assumptions. So first of all, that it is a steady state process. So it is not going to change in time. Then we say that kinetic energy and potential energy changes are negligible for hot and cold fluid. Then we also say that axial heat conduction is negligible. It means that all the heat which is being transferred, it is between the hot and cold fluid in the radial direction. So that is the predominant direction of heat transfer in this. And then number 4, we have got the outer surface of the heat exchanger is perfectly insulated. It means that all the heat lost by the hot fluid will be gained by the cold. So it means that nothing is being lost to environment. Okay? So all the heat which is being transferred from the hot fluid, that is going to be utilized to increase the temperature of the cold fluid. So now if we want to write the heat transfer rate for the hot fluid, we can easily write, we know the formula Q dot is equal to m dot h into C Cp h into Ph in minus Th out. So we here this subscript H is the represents the hot fluid, and because the temperature of the hot fluid would drop, so Th in minus Th out would always be a positive quantity. But usually, if we want to know the change in temperature, so change in temperature would be negative. Final temperature of the at the outlet, the hot fluid would have less temperature, so the heat would be lost from the hot fluid. So in that sense, it would be negative, and the heat which is gained by the cold fluid, that would be m dot c cp into t c out minus. So as we know that the because the cold fluid is gaining heat, so the cold fluid temperature at outlet would be greater than its temperature at inlet. So uh, now you can see that this temperature change, because Q dot H would be equal to Q dot C. So this temperature change is dependent upon this parameter, and then this temperature change is dependent on this. So these two quantities are called heat capacity rates. So we represent it with I write it heat capacity rate, that is the product of m dot into c. So here C H would be equal to, and that is represented with capital letter C. So CH would be equal to m dot H into Cp H, and similarly C C is equal to m dot C into Cp. So this heat capacity rate is the heat transfer rate which is required to change the temperature of a fluid moving of a fluid having a mass flow rate of 1 kg per second uh, by 1 degree centigrade. So that is the heat transfer rate required to change that temperature by 1 degree for a mass flow rate of 1 kg per second. So now we can simply write it like this: Q dot H is equal to Ph into Ph out minus Th in, and similarly Q dot C is equal to T3 into Th. T3, sorry, I think I have done a little bit mistake here in writing. It would be Ph in minus out, and here it would be T out minus T3. Right. So now you tell me that for a given mass flow rate, if CH is, let's discuss that where the temperature change would be more. Okay? If CH is more than CC, would it tell us? It would tell us that delta T C would be, which is this quantity. This is delta TC, and this is delta Ts. So delta Tc is more than delta Ts, right? Because this Q dot H is equal to Q dot C, all the heat which is lost by the hot fluid that is going to be gained by the cold fluid. So it means that if the heat capacity rate for the hot fluid is less, then the uh, heat capacity rate is more, then this temperature change would be less, because it would be less because this heat capacity rate is more. So it means that the cold fluid would experience a large increase in temperature. So because CH depends upon the specific heat and mass flow rate. So that is quite kind of understandable that if hot fluid is coming at a mass flow rate of 10 kg per second, and if the cold fluid, if it is coming at 1 kg per second, so uh, the 10 kg per second, maybe it would lose heat, but it would raise the temperature of the cold fluid by significantly large value, because its mass flow rate is 10 times less. So all the heat which is lost by that 10 kg per second hot fluid, when it would be gained by 1 kg per second of cold fluid, its temperature would rise more. So it means that delta Tc would be more as compared to delta Ts. So, but what will happen? Because okay, so this was just for simple heat exchanger where there is no phase. Now we talk about phase change heat exchanger. Any example of phase change heat exchangers? Anyone?
Condenser.
Condenser and boiler. Excellent. Correct. So we know that we have got uh, condensers, boilers, evaporators, all these are phase change. Now, in that case, we cannot use this formula. These formulas, they cannot be used in this case. Where there is a phase change, let's suppose that for the hot fluid, there is a phase change. Then we cannot use this formula. While that, if you remember Rankine cycle, if I draw for your uh, convenience here, if you remember, it was kind of Rankine cycle. Whenever phase is being changed, that is these are the processes from here to here. These are the phase change processes. So this is basically, if I write it, this is um, condenser, this is boiler, and this is boiling. So it means that delta T in the condenser would be 0. You can easily see. So if we write that Q is equal to C into delta T, which is the formula. C is the heat capacity rate. So C would be equal to Q upon delta T. Okay? So because delta T is 0, so C approaches infinity. Okay? So it means that heat capacity rate for any phase change process, that would be approaching infinity. So usually we use the formula Q dot is equal to M dot HFG for this. HFG is the latent heat of vaporization or latent heat of condensation. Okay, HFG is the enthalpy difference between this and this, or from here. So we use these two temperature difference. Right. So so for the phase change process, if we show that, if we want to show the condenser process on the on the on the uh, temperature profile curve, if we want to show that, just a condenser process, first of all, is we condense. So this is if we say that the steam which is going through the condenser tube, that would be at higher temperature. Okay, so this is inlet, this is outlet. Okay, so now the hot fluid is the steam inside condenser, and the water which is coming from the river or the air which is coming to take that heat, their temperature would increase, because that is at the temperature is not going to change for the this process, because this is a phase change process. So if you remember that for tube bank case, we also studied that the cold fluid which would come here, if we talk about the parallel flow heat exchangers, so they are going to go like this. Okay, because now we have got the hot fluid which is the steam inside the condenser. That heat would be taken by the river water or the air, by the flow of that, and their temperature would increase exponentially, which we have already studied in the tube bank case and the internal flow. And then the second process which we can show is the boiler process. Again, if you have got this inlet and this outlet, in this case, the steam which would be flowing through that boiler, that would be a, a cold fluid, because that heat, because the saturated water is being converted into vapor state. So it means that it is going to take heat from the some source. It can be by hot gases, it can be by combustion. So that hot gases would reduce, have a decrease in their temperature like this. Okay? This is the cold fluid in boiler, because that is going to be evaporated by the absorption of the heat from the that hot gases, or by taking that heat from combustion. Okay, by burning some fuel, so, or by a nuclear reactor or anything. So in that hot fluid would be that source from where the steam is taking heat and being converted into into the saturated vapor. So these are the two things which we discussed here. So now we are going to start with this discussion. We we are going to start log mean temperature distance. I think we can have 5 minutes break, and then we can start our discussion of log mean temperature. Thank you. Okay, ji. Welcome back after the break. So now we are going to start discussing the first method of analysis, which is called LMTD method, or we also call it the log mean log mean temperature difference method, and we call it LMTD method. Now, for this, uh, if we know that the here we need to determine the size of heat exchangers, and we are given the input and output temperatures of the hot and cold fluid. So let's suppose we have got uh, double pipe heat exchanger in parallel flow. In parallel flow, uh, which is having a parallel flow, having so we do the differential analysis here. So first of all, if we draw that, right? So here T is T H in. Here we have got T T in, and then here it is T C out, and here we have got T H out. Right? Better. So hot fluid is passing through this tube side, and this is passing through the shell side. We call it the cold fluid, and we take a differential element here. So we say that we have taken this differential element of the pipe, which is uh, of surface area ds. So now, if we want to see that how that temperature profile would be happening here, and temperature change for this kind of flow arrangement. So if we remember that the heat would be going from, if hot fluid is passing through this pipe, then it would be going through this cold fluid. Cold fluid is going through this shell side. Shell side. So if we draw that here, temperature distribution, it would be something like Now, if we see that differential element here, try to correctly somewhere. So we were here somewhere. So if we want to see this, right? So we are talking about the heat which is being, because the heat which is going to flow from this hot fluid, that direction would be like this. That would be delta Q. Delta Q, which is the heat which is going from the hot fluid towards the cold fluid, which is whose temperature is given here. Now, here this temperature difference. Now, let me focus again on this diagram. First of all, here we can see that there is some temperature change between this segment, this differential area. That is called, this thing is called DTH. DTH is the temperature change in hot fluid in that surface area, and then similarly we can define DTH. This distance is, this is DTH, which is DTC, because here if I write it again, first of all let me kind of, this is pH in, this is PC in, this is pH out, this is P out. Now this distance I call it delta T2, which is delta T2 is equal to TH out minus TC out, and similarly here I have got, this is delta T1. So delta T1 is equal to TH in minus TC. Right. So uh, delta T1, delta T2, and then I have also defined DTH and DTC. And here delta Q would be equal to, let me use the black pen instead. So if I write that delta Q, or uh, delta Q can be written in terms of hot fluid. So for the hot fluid, it would be equal to minus m dot h into Cph into dTh. Why I am putting minus here? Because you can see that dTh is being a negative value. So that negative value into this negative value, that delta Q would be a kind of a positive value. So similarly, delta Q can be written in terms of cold fluid, because all the heat which is being given from this hot fluid, that would be gained by this cold fluid. So that would be equal to m dot c into cpc into dt. dTc is the temperature difference between inlet and outlet. Outlet minus inlet for this segment. Right. So this we have written. So from here we can write dTh is equal to minus delta Q upon m dot H dTh, and similarly dTc is equal to delta Q upon m dot C Cp. Right. So now if we want to determine dTh minus dTc, that can be written like differential of Th minus Tc. That would be equal to minus delta Q. If we take, because we are going to write these two things, so delta Q can be taken, minus delta Q can be taken constant, and then we can write 1 upon m dot H Tth plus 1 upon m dot T Cp. Right. So why we have taken minus delta Q? Because we know that dTh is minus delta Q, so that would make it positive, and then because we are subtracting that, so here it would have been also minus, so that minus is taken as a common here, and these two terms are with the positive sign. Right. So now we can also write delta Q for this differential element, that can be written u into Th minus Tc into dAs. Right, dAs, what is dAs here? dAs, if I go back, sorry, if I go back here, dAs is this differential area of the pipe which we are talking about here, because we are doing differential analysis. So this red surface area is of that differential element which we have taken for the analysis of this heat exchange. So now we can replace delta Q here, this delta Q with this relation. So if we do that, we can write, sorry, B into Th minus is equal to U into Th minus T into DAS into 1 upon m dot H Cp H plus 1 upon m dot T. Right. So now if we rearrange it, we can write Th minus Tc divided by Th minus T. That would be equal to U into DAS 1 upon m dot H Tch plus m dot T Cp. Now, if we take the integral, if we want to do the analysis for the whole pipe, what we can do that here we can take the limits from in to out, and here the limits for the surface area would be from 0 to the length L of the pipe. So if we do that, we can easily see that let's hold it. And now for the left hand bit, we can see that it would be equal to log of t h minus t t c, and limits are it are out to n, and here it would become u into as 1 upon m dot s t t h plus 1 upon m dot c c c. Now if we do the simplification, we can write th out minus th out divided by this whole log of th thn minus, that would be equal to uas. Yes, so how it is as, because when we take the differential it would be length is pi dl, so that is ds is being replaced with that, and dot s and continue with this. Now, what is here UAS, or maybe if you remember in the beginning we mentioned that that Q H is equal to m dot H H into TH in minus TH out. So from here, if I write m dot H TTH is equal to Q dot H, we can say it Q dot would be the same thing, Q dot divided by TH in minus TH out. Similarly, Q dot is equal to m dot T. These are the relation we studied at the beginning of this class. So that was TC out minus TC in. So m dot T into TCC is equal to Q dot divided by TC out minus T. Right. So now these two things are going to be replaced with these two things. So if we replace them, we can write the left hand side would be the log term as it is. So log term would come like the same case here. So here we can write UAS into Q dot, and here it would be 1 upon TH in minus TH out plus 1 upon TC out minus T hold in. Let's see. Hold in. So now from here, if we want to calculate Q dot, we can write it, or maybe it was just a minute. Let me see. I think I have made a mistake here. Incorrect, because here this m dot h cph it is in the denominator, so it means that q dot would be in denominator and this thing would be the numerator. So here let me do the correction. This q dot shouldn't be here and this shouldn't be here. Just a minute. I hope that you understand that because it is in the denominator, it should be q dot would be in denominator. So I can write it like this, that it would be t h in minus t t h out divided by q dot plus t cold out minus t cold in divided by q dot. So q dot can be taken as a constant here. So we can say that q dot would be written here on q dot, and then here we have got the natural log term. Their term is, if we write it, th out minus t cold out divided by t hot in minus t cold. Now if we want to write q dot from here, we take log in the denominator here on the right hand side, and we take q dot on the left hand side. Now these steps are not very clear in your textbook, so I can write q dot equal to UAS into. Now I am going to rearrange it a little bit. So in a way that uh, I can write here I can write th in minus th in minus th out. So here I am going to write it th th in minus th in, and here I would write minus th out and minus th out, and then similarly here I would write natural log of th out minus th out. Okay, ji. Can anyone confirm that you can see, you can hear me?
Yes, sir.
Okay,
Yes, sir.
thank you. Okay, so I just lost the connection. Sorry for that. So we were deriving this equation. So
Yes,
here,
sir.
uh, so thank you for that. Okay, one thing maybe we might have kind of here it was minus delta Q. So when we have got that minus should be here. Okay, one thing I kind of it should be here, and then it should also be here. Which minus I am talking about? If I tell you again quickly, that in the derivation there was a minus here, so we need to keep that minus here in the derivation. So it should be somewhere. If I write it, it should be here, and then if we go down, come on. If we go down, this minus would be all along. It would come here, and then this minus would be here as well. Okay, so when this minus is here, I can write it here, and then it would be the last bit we were here at the moment. So it would be th in minus tt in. So if we take this minus here, if we take this minus, or we revert this log. So if we take the denominator as a numerator and then take this numerator into denominator, so it means that we are replacing this with like this. So if there would be a minus, so that minus would be cancelled out with this. So we can kind of we can we can just uh, make it positive by writing it th in minus. So we need to switch the denominator with the numerator and vice versa. So if we do that, here it would be th in minus tc in, and here it would be th out minus tc out. So if I take you back on the original figure where we started for the temperature distribution for the differential equation, for the differential analysis, if you see here, Th in minus Tc in is delta T1 and Th out minus Tc out is delta T2. So here we can say that we can write Q dot is equal to UAS delta T1 minus delta T2 delta T2 divided by natural log of delta T1 upon delta T2. And this thing is called UAS into delta T logarithmic. So that's why the name of this method is log mean temperature difference, because we are talking about log mean, not the simple mean. So that's why this is the uh, this is the method name, and then we derived it for the parallel flow arrangement. But the same relation can be derived for the counter flow arrangement. So in the counter flow arrangement, what would be the difference thing? that would be kind of one thing would that would be in that case it would be. Let me go to the figure. It's taking some time. Okay. So for the counter flow heat exchanger, then this TC in would be somewhere here. If I kind of draw that with the blue dashed line, so that would be something like this. In that case, the TH in TH out would be something like this, and that would be something like this. Okay. In that case, this would, if this is TH in, TH out would be the same, but in that case, TC in would be here, and core temperature outlet would be here. And then we can apply the same procedure as we did for the parallel flow, and if we do that, we would be able to get to the same relation which we have gotten from the parallel flow heat exchanger. So, uh, so if I can quickly go through the lecture slides which we have covered up till now. So we talked about two methods. One is log mean temperature difference. It is used to calculate a specific temperature change in a fluid stream, and we need to calculate the surface area which is required for that specified temperature change. And in effective NTU method, the surface area of the heat exchanger is given as input, and we use to predict the outlet temperature of heat and these things. And then these assumptions we wrote on the whiteboard, and then we discussed about the heat capacity rate. It is the product of the mass flow rate and the specific heat. And then we discussed about these definitions, and then we can write it in terms of specific heat rate. Then we discussed that this CH and CC would determine the temperature change. If CH is more than CC, then temperature rise in the cold fluid would be more, and vice versa. And then we discussed about the phase change process, that in the phase change process we calculate Q dot is equal to m dot HFG. Then we started the this discussion. So because this figure looks quite complex here, so that's why I just thought that we can do it in a simplistic way. We did did this temperature distribution profile on the whiteboard, and then we did all this derivation as I have shown you, and in the end they have just at this point we replace it with q dot into dh in minus at this place, and then if we do the simplification we can write q dot is equal to UAS delta t log logarithmic and delta t1 minus delta t2, and then this can be equally applicable for the counterflow heat exchanger. The only difference is the direction of flow is opposite in the counterflow, and if we have been given a size of heat exchanger, if the length of these two heat exchangers in the parallel flow and counterflow are equal, then the temperature rise would be more for the counterflow. So usually in practice, in industry we use counter flow heat exchanger more rather than the parallel flow. Parallel flow for it is good for just theoretical understanding of things, but practically if for a given temperature change, if we want to determine the length of the pipe for the counter flow heat exchanger, the length of the pipe requirement would be less. The reason for that is that because if you look at the at the temperature profile for both cases as we discussed in the beginning, if I go there, here the temperature change is rapid in the beginning, but as we move along the tube length it decreases very rapidly. But for the counter flow heat exchanger, this temperature this difference in temperature remains constant. So that's why when we talk about big heat exchangers, very long pipe heat exchangers, this would always give us more heat transfer in case of counterflow heat exchanger. So in practical devices, usually we have counterflow heat exchangers installed. And I think we have almost at the end of the class. So in the next class, which is tomorrow, we are going to do some numerical problems. So all this analysis that has been done for a single tube, so we would extend it for the shell and tube heat exchanger and multi-pass heat exchanger. Multi-pass in which we have got more turns in tubes. Inside the shell, we have been kind of a number of tubes. So how can we apply this analysis for that practical case? So hopefully things are a little bit clear. Maybe if you have got any query, you can ask. Let me download the attendance, and then if there is no further query, then maybe you are free to leave. So I have downloaded the attendance. So if there is any further query, you can ask. So if someone wants to leave now, is okay with that. So